In our next set of videos, we are going to focus on enolates. And so we're going to talk about the acidity of alpha hydrogens and then talk about applications. One quick one is the haloform reaction. And then we're going to talk about the alkylation of enolates, both with direct alkylation and some indirect methods called the acetoacetic ester synthesis and the malonic ester synthesis. In this video, we're going to start looking at the acidity of alpha hydrogens, but before we get started, I wanted to focus on alpha hydrogens. So throughout this year, we've seen a few cases where we rely on Greek letters to be able to talk about a particular position. If we were to think about IUPAC naming, there's a whole set of rules we know in terms of IUPAC naming. And so for this compound, this is carbon 1, 2, 3. For the next compound, we have 1, 2, 3, and then the last compound, this would be carbon 1, 2, 3, 4, 5, 6. If we were to compare these two aldehydes, well, this is the carbonyl carbon is carbon 1 and carbon 2 is adjacent to the carbonyl, and there are special characteristics of this carbon and of this set of hydrogens. So we could always refer to carbon 2. But when we talk about ketones, well, in this case, carbon 2 is not the one adjacent to the carbonyl, but it is the carbonyl. Rather than referring to the numbers, we are instead going to name our positions. So focusing on the carbonyl carbon, the adjacent carbon is the alpha position, beta, gamma, etc. With the next aldehyde, this is our focus, and so alpha position and beta position. For the ketone, this is our focus, and so this is an alpha position and this is an alpha position. And on the right side, we also have a beta, gamma, delta. So it's important to be able to refer to the alpha position because there is special reactivity of the alpha position. So the special reactivity that we'll be looking at is the acidity of alpha hydrogens and then the reactivity that results because of that. Now we want to consider the acidity of alpha hydrogens, but let's start out with a more comprehensive review of some pKa values. So for a typical carboxylic acid, this has a pKa of approximately 5. An alcohol, we're looking at about 16 or 17. An alkyne, this has a pKa of about 26. An alkene hydrogen, this is about 45. And an alkyl hydrogen, this has a pKa of about 60. So typically, a hydrogen that's connected to an sp3 hybridized carbon is a very, very weak acid with a pKa of about 60. But if we have a hydrogen connected to an sp3 hybridized carbon that happens to be next to a carbonyl, now we're not talking about this situation, we are talking about the alpha position. And the hydrogens that are alpha to a carbonyl have special acidity. So for example, a hydrogen that is alpha to an aldehyde, this has a pKa of approximately 17. And next to a ketone, these are around 19. So they're still kind of weak acids, but much, much stronger than other hydrogens connected to carbons, right? Closer now to alcohols. So that is a significant difference. When we talk about a hydrogen that is alpha to an ester, these have pKa's of about 25. And a hydrogen that is alpha to a nitrile also has a pKa of about 25. When we have a beta dicarbonyl compound, so focusing on this position, this is the alpha position and the beta position, and there's another carbonyl. When we have a beta dicarbonyl, that means that we have a set of hydrogens that are alpha to this carbonyl and this carbonyl. So the features that make these more acidic than these, well, we've got twice those factors affecting this set of hydrogens. So a set of hydrogens that is between two ketones, this has a pKa of about 9. If these hydrogens are in between a ketone and an ester, now we have a pKa of about 11, so these specifically. And then a set of hydrogens that are between two esters, these have a pKa of about 14. Now, for comparison, let's think about some bases that we have talked about. And what we're looking at here then would be the pKa of the conjugate acid. So hydroxide, we're comparing water, which has a pKa of 15.7. Methoxide, we're comparing methanol with a pKa of 15. Ethoxide, ethanol is 16. LDA is lithium diisopropyl amide. So it looks like this with the lithium as the counter ion. The diisopropyl amine, its conjugate acid, has a pKa of 36. So it's helpful to keep in mind the strength of bases as we think about the acidity of particular acids. But before we move on, it's important to think about why alpha hydrogens are significantly more acidic than other hydrogens that are connected to sp3 hybridized carbons. Well, part of the reason is inductive effect. When we focus on the carbonyl group, we know that the oxygen is pulling away electron density from the carbon, and this sp2 hybridized carbon will be then trying to pull away electron density from its neighbors. So pulling away electron density from this carbon means this carbon's going to try to pull away electron density from this hydrogen, and so that is going to weaken the carbon-hydrogen bond, making it easier to break, making this more acidic than what we have over here. So inductive effect, we're really talking about differences in electronegativity, but remember, inductive effect falls off quickly with distance. So these hydrogens are more acidic because of the electron withdrawing carbonyl, same thing here, and these are more acidic because of the electron withdrawing nitrile. Here, this set of hydrogens is made more acidic because of the electron withdrawing carbonyl and the other electron withdrawing carbonyl. Same thing here and here. The other important factor that accounts for the increased acidity of alpha hydrogens is resonance. Let's take a look at this aldehyde, for example. And if this reacts with a base, then the base will pull off one of these protons, put these electrons onto the carbon, and we get this enolate. Wait a minute, why am I calling that an enolate? Remember, this structure is a resonance structure, and we can draw another resonance structure. Let's imagine that these electrons move here, and these electrons move here, giving us another structure that looks like this. So now we have the alkene and the alcohol, but with a negative charge, so this is called an enolate. With a hydrogen connected to a regular sp3 hybridized carbon, if this proton is removed, these electrons just sit on this sp3 hybridized carbon, and that is very unstable. But here, these electrons, although we can draw them sitting on this carbon, we need to remember that this does not exist, and what actually exists is a hybrid where these electrons are spread out between the carbon-carbon and oxygen, and therefore the negative charge is spread out between this carbon and this oxygen, which stabilizes the conjugate base which therefore makes the acid more acidic. Now, if we think about the different resonance structures, having a negative charge on an oxygen rather than on a carbon, this is better, which means this resonance structure is going to contribute more to the resonance hybrid. However, as we're going to see in a little bit, the reactivity of enolates usually looks like this. And so it's a source of a nucleophilic carbon. And so even though the resonance hybrid looks more like this, I like to draw them like this because it helps me to think about the reactivity. Either one is acceptable. You need to remember that what actually exists is the resonance hybrid. On the last slide, I asked you to think about pKa values because we need to think about position of equilibrium. So here we have a number of different carbonyl-containing compounds reacting with different bases. So first of all, let's write out the products of each acid-base reaction. In our first example, hydroxide can grab off one of these alpha hydrogens, and that will give us the enolate plus water. In the second example, amide is our base. We'll grab off an alpha proton, giving us the same enolate. But in this case, the conjugate acid is ammonia. In the third example, diisopropyl amide is our base, grabs off an alpha hydrogen, giving us the same enolate, but a different conjugate acid. Now let's think about pKa values and therefore the position of equilibrium. So for a ketone, the alpha hydrogens have a pKa of about 19. And in comparison, water has a pKa of 15.7. Ammonia is about 36. And any amine is also about 36. So this is a slightly weaker acid than this one is, and so the equilibrium lies a little bit to the left. In the second and third example, this is definitely the stronger acid. This is a much, much weaker acid, so the equilibrium lies to the right. Now, in each of these cases, let's think about what exists at equilibrium. In the second and third example, because the pKa values are so different, and this is a much, much, much weaker acid, then the equilibrium lies very, very far to the right. So at equilibrium, we have lots and lots of enolate and very little ketone. In our first example, though, because the equilibrium lies a little bit to the left, that means that the majority of this compound exists as the ketone and a much smaller amount exists as the enolate. But we do have a significant amount of enolate even in this case. So that's important to think about. We do have a significant amount of enolate, which could potentially go on and do other reactions, even though the equilibrium lies to the left, and therefore the majority of this compound exists as the ketone. Next, let's take a look at some esters. Methoxide can act as a base, grab off an alpha hydrogen from here, giving us this enolate. And in the second example, LDA, this can act as the base, grab off a proton from the alpha position, giving us the same enolate. Plus diisopropyl amine, and sorry, I forgot to write it for the first one, plus methanol. Our pKa values, esters have a pKa of about 25. In comparison, methanol has a pKa of about 15. And so methanol is the stronger acid and equilibrium lies to the left. Diisopropylamine has a pKa of about 36, so the ester is the stronger acid and equilibrium lies to the right. So in the case of an ester with an alkoxide, the equilibrium lies toward the ester, which means we have lots and lots of ester and a very small amount of enolate. Even though it is, in comparison, a much smaller amount, it is still an appreciable quantity such that it can move forward and do other reactions. In the case of LDA reacting with an ester, now the ester is the stronger acid, so equilibrium lies to the right, and that means we have a little bit of ester and lots more of the enolate. Now, before we move forward, let's think about other types of reactions, because a few chapters ago we looked at reactions where we had a nucleophile adding to a carbonyl carbon. Now we're talking about a base/nucleophile not adding to the carbonyl, but instead grabbing off a proton from adjacent to the carbonyl. The thing that's important to keep in mind is that all of these reactions are at equilibrium. And so it is possible that hydroxide, for example, will act as a nucleophile and do nucleophilic addition. And so we're going to have some of the hydrate species, but then that can equilibrate back to the ketone can equilibrate to the enolate can equilibrate back to the ketone, which can be converted to the hydrate again, right? So these molecules are all going to be going back and forth. And the position of equilibrium, well, even this position of equilibrium doesn't matter completely until we think about what else happens, right? If we add something else, then if a little bit of this reacts, it will go on to make something else, maybe that isn't at equilibrium, or maybe such that the equilibrium lies toward this other product that we're not yet specifying. With these two examples, they have similar acid strength, and so these are about the same base strength, and so both of them could potentially act as nucleophiles as well, but here, because this is so big and bulky, it will be much less likely to act as a nucleophile, much more likely to act as a base. What about when we are looking at esters? Well, same thing here. LDA, nice and strong and bulky, so this is much more likely to act as a base rather than acting as a nucleophile to do nucleophilic acyl substitution. In the case of an alkoxide, well, this is quite likely to do nucleophilic acyl substitution. So let's look at what that would mean. If methoxide acted as a nucleophile rather than acting as a base, then these electrons would add here, push these electrons up onto the oxygen, and then those electrons will collapse back down and kick out the methoxy group as a leaving group, and what we end up with is the exact same thing. So rather than trying to avoid nucleophilic acyl substitution, well, we just know it's going to exist, so let's make sure that even if it exists, that it doesn't interfere. So if nucleophilic acyl substitution gives you the exact same thing, then there's really no change until something else happens. If we had a methyl ester and we used ethoxide, then we're going to have a problem. And so you always want to choose your alkoxide to match the alcohol part of your ester. And this is why up here we might think about using hydroxide, but down here if we used hydroxide, then we would get some nucleophilic acyl substitution leading to hydrolysis of the ester, and so that would interfere with any reactions that can happen with the enolate. So a few things that are important then to keep in mind. Next, let's take a look at some acid-base reactions of a few of our beta dicarbonyl compounds. So if we have a beta diketone and we react it with hydroxide, well, the most acidic hydrogens are these, and so this is the enolate that can be formed, where one of the center hydrogens has been removed. And water is the conjugate acid. In the second example, we have methoxide. Notice we have an ester, so if this was to do nucleophilic acyl substitution, we would end up with the same thing. So we don't worry about it. But it gets interesting when this acts as a base, grabs off this proton, giving us this enolate plus methanol. And in the third example, once again, we have our base matching our ester. So when this acts as a base, it can grab off one of these protons, giving us some of this enolate plus methanol as the conjugate acid. If we think about pKa values, a beta diketone has a pKa of about 9, a beta ketoester is around 11, and a beta diester is about 14. Water, we're looking at 15.7. Methanol is 15. So in the first example, this one is our stronger acid, so the equilibrium lies to the right. In the second example, this is our stronger acid, so again, the equilibrium lies to the right. And in our third example, not as much of a difference, but still this one is the stronger acid, and so once again the equilibrium lies toward the right. So in each of these cases, at equilibrium, we are going to have lots and lots of enolate and a smaller amount of our starting material. Often we are going to think about these kind of qualitatively, but let's for a moment think about it quantitatively. And as we think about an aldehyde reacting with hydroxide, well, the hydroxide will grab off a proton from the alpha position, giving us this enolate plus water. And because we're talking about a pKa of about 16 compared to 15.7, the equilibrium lies just a little bit toward the left. So the position of equilibrium is to the left. What exists at equilibrium? Well, this is going to be a mixture of both the aldehyde and the enolate. Right? So usually we want to think mostly qualitatively, maybe a little bit in terms of relative concentrations. In this case, we're going to have a little bit more aldehyde than enolate. But what if we need to focus quantitatively? Okay, how much do we actually have? Well, let's think about the equilibrium constant for this reaction. So the capital K, this would be equal to the concentration of enolate, we don't use water, divided by the concentration of aldehyde times the concentration of hydroxide. And what's been shown experimentally for this particular reaction is that the rate constant is equal to 0.5. So at equilibrium, we're going to have about 2 molecules of aldehyde for every 1 molecule of enolate. But what this really means is that at equilibrium, we have a significant amount of both species. By the way, for the equilibrium constant, this can actually be derived from the pKa values if needed. If we look at the example of an ester, so this base can grab off an alpha proton, giving us this enolate plus methanol. Here we have a pKa of about 24 compared to 15. And so this is the stronger acid. Equilibrium lies to the left. Now in this case, the equilibrium constant K is equal to 1 times 10 to the negative 9. So here, our ratio of ester to enolate is on the order of 1 billion to 1. So lots more ester than enolate. But still, if we think about having a mole of ester in our overall reaction, even though this is a relatively small number, we're still talking about trillions of molecules of enolate. So have that general idea of the numbers of the ester compared to enolate or the aldehyde compared to enolate. Have that idea in mind as we move forward to look at reactions of enolates.